It's an honor and a privilege to have Professor Alain here with us. He is the Nobel Prize of Physics in 2022, as you know, but more important than that, he was telling me just a couple of minutes ago, he is a professor, and he likes to explain things. Is that right, Professor? So thank you very much for accepting the invitation of being here today with us in our 113th anniversary. I must tell just before I leave the floor to Yasser Omar that I've never seen this place with such a crowd. It's totally filled, and we have people in the stairs. So that results in the fact that I have make an invitation to Professor Alain to be our guest professor because we need students in classes. So I think Professor is thinking about the invitation, so thank you very much and for being with us today. Yes, sir. Yes, sir. The floor is yours.
So, hello everybody, welcome. Thank you very much for attending. Thank you very much, Rogério, for being here and welcoming us. Happy birthday to Técnico. It's a great pleasure to have you here. You said you've never seen this so filled. I mean, we had to stop, we received 380 registrations, and then we stopped getting registrations because the waiting list was being too large, so we would like to welcome more people, but this was what was possible, but we are going to record the session and then make it available online for those who couldn't attend to attend it. So thank you very much for being here, everybody. Also, thank you very much to the team who organized the logistics. I just want to briefly introduce you the Portuguese Quantum Institute. This is both the PQI colloquium and an IST distinguished lecture by Professor Alain. The Portuguese Quantum Institute is an organization who has 3 founding members, Técnico, Instituto Portuguese Quantum and Deloitte, and it's open to other members who may want to join. And it has 5 goals. Its aim is to develop quantum information science and technology in Portugal and beyond Portugal in 5 important dimensions. The core, I would say, it's research, but we care also about innovation, policy, education, and outreach. So I very briefly tell you what we do. We work on quantum computation, quantum internet, energetics of quantum technologies, and we also support some experimental efforts being developed here at CeFEMA in Técnico and also now at Deloitte. We're organizing the European Quantum Technologies Conference here in Lisbon in November, so I welcome you to participate. We also try to work on innovation, and so we want to announce today that under the leadership of Mário Caldeira, we are launching the Portuguese Quantum Innovation Center. This is a forum where we want to bring together companies and public entities so that they can be up to date to the developments of quantum technologies. In my vision, there's an ongoing revolution. I don't know the consequences, but I think nothing will be the same as before. To collect their inputs and their use cases, who are actually precious, both here and at international level, to inform them of funding opportunities and foster collaborations and also manage internships for students in these entities. So very happy to announce this today here. We also work on policy, for example, and so this is a very large and multidisciplinary team, very multidisciplinary, not large yet, and you're welcome to join, but very multidisciplinary. And so, for example, it's the Portuguese Quantum Institute that does the yearly monitoring of the key performance indicators of the European program in quantum technology. So we're talking about a program that by now goes around 8 billion euro, and so this is done here from Portugal. We bet a lot on education, and we have some partners here today, some school teachers. We have created what we call the network of quantum schools, Rede de Escolas Quânticas. We have schools in the whole of Portugal, in the continent, in the islands, and we have schools also in Portuguese-speaking countries in Africa and in Brazil, and we really want to engage and interact with school children and school students and school teachers, and we have some of our partners here today. Also, I want to announce that we are going to launch today the PQI Quantum Talents Program under the leadership of Margarida Abcacis. These are a small initial set of scholarships for very talented undergraduate and master students to develop a research project in quantum science and technology here in Portuguese universities. I go a bit fast because the most important, of course, we want to listen to Alain, but I want to connect to that. We're also very active in scientific outreach. From here and together with colleagues from now, I think more than 70 countries, we have launched the World Quantum Day, celebrated on the 14th of April, but in fact celebrated in the weeks and months around. And this was pre-launched with Alain. So during the pandemic, Alain Aspect kindly accepted to give a very nice online talk, which is on YouTube. You can watch it. And these colleagues from all these countries, they came together, and this was our announcement to the community, to the world. We want to celebrate quantum science on and around April 14th every year. And so thanks, Alain, for your help on this. It became a very successful endeavor. So this is today the closing event of the World Quantum Day 2024. As I said, this is not only celebrated on April 14th, but on the weeks around it. So this today is the closing of the events of 2024. Here we have the numbers from last year. We're still processing the numbers from this year, but we had essentially events in all the continents. Even President Biden wished a happy World Quantum Day. Yes. And so, yeah, I invite you to celebrate the World Quantum Day in 2025. This is a bottom-up initiative, and in fact, we're working hard that, so I have this colleague from Brazil, from Rio de Janeiro, Marcel Santos. We were deciding the date for the World Quantum Day, and he said, well, I'm a quantum physicist. For me, every day is a quantum day. So this became our slogan, and we're working hard to make 2025 the quantum year so that we can have 365 days of quantum days. Let's see. And finally, we have established a program we call the Young Ambassadors of the World Quantum Day that we are pioneering here in Portugal. With these student associations, and others are welcome to join. So we have students from the Faculty of Sciences in Lisbon, in Porto. We have Nefist here. We have from the Faculty of Sciences of Universidade Nova. We have it's not here, Fizua from Aveiro, who may be calling me, sorry for this, and the Association of Physics Students and other organizations of students. So thank you very much for participating. The goals of the Portuguese Institute is to, sorry for this, I should have turned off the sound, to work for our members, so Técnico, IPQ, and Deloitte, but also to contribute to develop this field in Portugal. We want to have a presence in Europe and beyond. So thank you very much for coming, and now it's my great pleasure to introduce Alain Aspect. So Alain Aspect is at l'Institut d'Optique and Université Paris-Saclay in France. He made very pioneering and important and against the current experiments to understand quantum entanglement in a period where this was not taken as seriously as it should. And thanks to his pioneering vision, courage, and intellectual capacity and experimental capacity, he proved those findings and helped us understand entanglement. And of course, for that, he's been laureated with the Nobel Prize of Physics together with other colleagues, but he continued very active in opening other fronts of research, in particular using cold atoms for quantum information processing, for quantum simulation, for some fundamental understandings of quantum mechanics. So it's a great honor and privilege to have you here today, and so that all these colleagues and audience can listen firsthand to the work you've been done and the vision you have for quantum physics. So thank you very much, Alain, for being here.
Non, il était au fond de ma poche, je crois. C'est que j'ai trop de choses dans la poche. Voilà. Pas de commentaires. Mon épouse fait des commentaires.
de vrai.
Of course, this worked when we tested. I think it's Alain trying to send us a message. He's a co-founder of a quantum computing startup. He's trying to tell us quantum computers are better than these classical machines, but not.
You know, I needed help of a theory guy for hooking up. We experimentalists, we always need some input from theory. Okay, thank you very much for this nice introduction. It's a great pleasure to be here. Those of you who looked carefully into the announcement may have remarked that I have slightly changed the title because I've been told that there are some real general public people here in the room. So initially I planned to make a usual colloquium, that is to say addressing, let's say, kind of advanced scientists, and I changed it to a talk which is more directed towards people with less education. It will be a little more general, although my wife, who, in spite of being a scientist, says that it is too difficult. You will tell me at the end. You can make a poll, okay? Was it too difficult or not? Okay, so I'm going to talk of two quantum revolutions, and I want to emphasize that Einstein was really crucial in the two quantum revolutions, in spite of what some people think. Some people, at least when I started my work 40 years ago, many people told me, oh, you know, Einstein was great in discovering relativity, but he never understood anything in quantum mechanics, which is totally wrong. He played a major role in the first quantum revolution and a major role in the second quantum revolution. So I'm going to tell you that. Moreover, those of you who speak French, you can order a small book by me, Einstein et les révolutions quantiques, and maybe it is already translated in English. Maybe you could translate it in Portuguese. You could do it before the Spanish people, okay? Let us start. So I'm really delighted to be here. I have had several outstanding collaborators coming from Portugal. One of my best PhD students in the last decades, Rafael Lopez, came from Portugal. Now he's with CNRS in France, but okay, you lost him. But if you can get him, I can tell you, he's one of the best experimentalists I had ever in my group. Okay, let us start. First, because we have general public, let me emphasize something. Quantum physics is definitely strange, but strange does not mean irrational. What is quantum physics? It's a mathematical formalism which allows us to perfectly describe observed facts impossible to describe in classical physics. I will come back to this, stability of matter, etc., etc. It's a mathematical formalism allowing us not only to describe what we know, but it also allows us to predict new phenomena that are observed later. A best example is entanglement. Entanglement was in the equations of quantum physics. Nobody had thought about entanglement, and we, not only me, but several groups, we went to the lab and we observed entanglement, which was in the equations. Finally, it's a formalism which allowed creative physicists to invent new devices, transistors, lasers, integrated circuits. You see what is at the root of the new society of information and communication. Young people don't think that the society of information and communication was always here. When we were young, and when I say we, some of them in the front row also, okay, there was no cell phones and no internet, no highway for information and stuff like that. And this has been permitted by transistor, laser, integrated circuits, the fruit of the quantum revolution. What is the problem with quantum physics? We have no simple image to represent the formalism in our usual space. This is what makes it strange. But once again, strange does not mean irrational. We have a perfect formalism for describing things. And we have some images which are a little bit crazy. I will show you at the end. Okay, let us start. And do not draw nonsense consequences. You will from time to time look into the newspaper or see in the newspaper, they are reporting something which is totally crazy, okay? And they say, oh, it's quantum. It can be explained by quantum physics, which is absolutely nonsense, okay? So it is not because it is strange that it is quantum. Quantum is strange. Okay. So I'm going to talk of the first quantum revolution and then of the second quantum revolution. And we have two concepts. Everything in physics starts from basic concepts. We have two concepts at the root of the two quantum revolutions. At the root of the first quantum revolution, we have wave-particle duality. The heroes are Einstein and Louis de Broglie. And at the root of the second quantum revolution, we have entanglement. The heroes are Einstein with his colleagues Podolsky and Rosen, and Schrödinger the same year. And then 30 years later, 29, John Stuart Bell. These are the heroes of the second quantum revolution. Let us start with the first quantum revolution. Quantization. Why do we speak of quantization? We speak of quantization because people at the beginning of the 20th century realized that some quantities that we consider continuous, able to take any value in the classical world, some of these quantities, in fact, can take only some specific value. We speak of discrete value to say only a finite number of such values. Example, light. Classically described as a wave, giving interference, diffraction, and plenty of things known about waves. They also must be considered as a beam of particle with a well-defined energy. So we have grain of energy rather than a continuum. Who discovered that? Planck. But Planck did not really believe in what he said. It's clear that he did not want to see really what he has done. And the first one who realized that was Einstein in one of these famous papers of 1905, where he introduces the notion of quantum of light, least quantum, named later photon. Okay. But Einstein, who was a good physicist, also knew that there are phenomena like interference, diffraction, that you can describe only by assuming that light is a wave. So on the one hand, he has very good reason to say light is made of photons, well, least quantum. On the other hand, he has good reason to know that light must be described as a wave. Conclusion, he was the first to speak of wave-particle duality, which is not only words, but which was several reasoning in one of these wonderful papers of 1905, several lines of reasoning, arguing, say, look, in this experiment, on the one hand, I have this, on the other hand, I have that, so light is both a wave and a particle. And you know, he got the Nobel Prize for that, not for relativity. He got the Nobel Prize for his model of quantizing light. Okay, so wave-particle duality first introduced by Einstein. Then for light, then matter. Quantization of matter. Physicists, as I told you at the beginning of the 20th century, they had problem to understand some phenomena, and among the phenomena, the stability of matter, and when they were studying the light emitted by atoms, what we call the atomic spectra, but it is the analysis of the light emitted by atoms, they came to the conclusion, well, Niels Bohr came to the conclusion that to understand that, you have to admit the following model for the atom. You have a nucleus with a positive charge, attracted electron with a negative charge. You know that positive and negative charge attract each other, so the nucleus attracts the electron. And it turns out that the law of attraction is the same as gravitation. It goes as the inverse of the square of the distance. So you can think of trajectories, just like satellites around Earth or like planets around the sun, okay? But in order to understand the spectrum of light, you have to accept the idea that only some of these trajectories are allowed. If you think of satellites around the Earth, you can basically put them at any altitude. Okay, well, not too low because there is friction of the atmosphere, but you can put them at any altitude. Here, it's not the case. The electron, you can have them only at a certain distance from the nucleus, and in order to understand that, you need, just to see if you follow, quantization. Quantization, how does it work? Wave-particle duality for matter. You have to admit, following Louis de Broglie in 1923, that when you have an electron on its trajectory, you must also think of it as a wave. And if you have a wave on a trajectory like that, if you want to have a steady situation, a stable situation, you need the wave to recouple on it on each turn, okay? So you need to have an integer number of wavelengths on this trajectory. Just like your guitar, why do you have a sound? Because you have an integer number of, well, half wavelength, but here is full wavelength. So this quantization of matter, admitting that electrons, which are particles of matter, are also waves, is the key to understand the Bohr quantization condition, and so to understand the structure of matter, the spectrum of light emitted, etc., etc. I like these photos. Why do I like these photos? Because they are happy, young people. Look how quantum physics is nice. These people. You should study quantum physics. Look, this is Louis de Broglie. Okay, looks a little like Groucho Marx. Huh? Don't you think so? Yeah. And this is Schrödinger. And you see, in spite of his equation, which looks complicated, he is very happy that he found this equation. Okay. Wave-particle duality. It's strange. How can a thing be both a wave, propagating everywhere in the room, and a beam of particles? Well, I don't know what to answer other than to say, let us do an experiment. And this is an experiment that we did with my first PhD student, Philippe Grangier, in 1986. We claim that we were able to emit individual photon. We say, okay, it was the first time, okay, nobody had never built a source like that. We say, okay, our source does emit individual photon, one, and then the next one, and then the next one, reasonably well separated, okay, not both at the same time. To show it, we invented this device. We send our so-called single particle, we want to prove it, on a beam splitter. And if a wave arrives on a beam splitter is a piece of glass, okay? You see a ray of sun arriving on a piece of side, a fraction is transmitted, a fraction is reflected. But if it is a particle, it will not be partly transmitted and partly reflected. It will be either reflected or transmitted. And if it is the case, then we are going to find that the probability of joint detection that I can find with an electronic circuit called the coincident circuit that allows me to know if I have two joint detection here and there, we are going to find that never happens. This shows that indeed it is a single particle. Now I don't have yet wave-particle duality. Second experiment, same source, same beam splitter, same mirror here, but now, rather than putting a detector here and there, we recombine the two beams. And now, people who have studied a little bit of optics and remember the course of optics, say, oh, this is an interferometer. I have a wave split into parts, recombined here, and then according to the difference between the length of this path and the length of that path, I will get light more here or more here, or somewhat in the difference. And so if I slightly move this mirror, I change the difference, and what I observe, you will see. So now I say I have a wave, split in two, recombining, and I observe interference. we did observe interference with our source and our single photons. Which means that, of course, because we have only one particle, we cannot observe it like that. We have to repeat the experiment many times, and for a certain position of the mirror, we observe the light here. For another position of the mirror, we observe here, and when we change the position of the mirror, we have this modulation. So you see, the same source, emitting the same so-called single photon wave packets. On the first experiment, the single photon wave packets behave as wave, go either on one side or the other one. In the second experiment, the same object behaves as a wave, is split in two and combined. I suppose I did something wrong for the first. In the first one, it's a particle, and in the second one, a wave. Excuse me. So, what do you do with that? It's puzzling. It's really strange. Well, you read Bohr, and there is something famous in Bohr philosophy or epistemology, let's say philosophy of physics. It's called complementarity. Niels Bohr said, okay, good. Well, he never saw this experiment, but he anticipated the result. He said, good. You know, there is something important. You have to choose. Either you do the first experiment or you do the second one, but you cannot do the two together. So you have to choose. So the contradiction or the inconsistency is not as bad as it looks because you have to decide. There is one point where Bohr was really going a little too far when you consider the second quantum revolution and you consider entanglement, is that he insisted that in fact it is the measuring apparatus that determines the nature of the object that you look at. And in this you can swallow that. But with two particles and entanglement, you will see that it is more difficult to swallow. Anyway, this is the first quantum revolution, this wave-particle duality, and we have to acknowledge that this first quantum revolution is absolutely fantastic. It was a conceptual revolution, wave-particle duality. It was a scientific revolution because it allowed us to understand the structure of matter. Let me emphasize a little more that structure of matter. People knew at the end of the 19th century that matter is made out of positive and negative charges. And they knew that positive and negative charge attract each other. And then comes the question, why does not matter collapse? You know, positive, negative should collapse. Why doesn't it collapse? And the answer is quantum physics. It's because if you try to get the distance between the electron and the nucleus very small, it means that you have to describe the electron with a wave which has a smaller and smaller wavelength. And small wavelength means a lot of energy. Where is this energy? Well, you don't have it, so the electron will remain at a certain distance. Of course, you can use Schrödinger equation, make a full calculation, but just the fundamental thing is that because the electron is a wave, you cannot confine it too much, so matter does not collapse on each other. Okay, so you can understand with quantum mechanics, mechanical, electrical, optical properties, and you can also understand exotic properties of matter that were first discovered by experiment, superconductivity and superfluidity. You know the fact that when you go at lower and lower temperature, for instance, a piece of metal becomes infinitely conductor. Okay. I already said that not only it's a conceptual and scientific revolution, it's also a technological revolution because based on wave-particle duality, people invented laser, transistor, integrated circuit. I like to emphasize this point. You know, transistor was not invented by a bright young guy in a garage in California. It was invented by the greatest physicists of that time, trying to understand exactly how electrons propagate in matter and making theory for that. And eventually, they invented the idea of transistor and then realized it. Same for laser, same for integrated circuit. And by the way, there was a Nobel Prize for each of these inventions. Nobel Prize for laser, for transistor, for integrated circuits. Okay. So I insist on the fact that it is a fruit of this conceptual revolution and not just invention at random like that. Okay, so this was the first quantum revolution. I promise you to say a little bit about that. And now let us switch to the second quantum revolution. The second quantum revolution is based on the concept of entanglement. What is it? I'm going to describe an experiment, and I'm even going to educate people who do not know about the Dirac notation, because the Dirac notation is so beautiful that there is no reason not to believe that in addition it's simple and everybody, even you, can understand it, okay? First, I have to explain what I am going to do to each of these photons. I have a photon going to the left, a photon going to the right, and I'm going to do polarization measurement. What does it mean? Well, I should have brought, I have a laser with me, but I was afraid that in the plane they think that I am going to commit some kind of terror, so I left it home. So the idea of measurement of polarization is the following. I have a wave propagating, okay, and the structure of the wave is such that there is the essential is an electric field vibrating perpendicular to the wave. And so the electric field can have any direction perpendicular to that, which means that I describe it in a plane by a vector with two components. So it can be, for instance, described with a component along this axis and a component along that axis. Now I have a polarizer, which is a device which allows me to know what is the direction of vibration of the electric field. So I put my polarizer, it has an axis like that. If the vibration of the light is parallel to this axis, it will go up in channel +1. If the vibration is perpendicular to the axis, it will go down in channel -1. You see, channel +1, channels -1. Now, if my beam is polarized at an angle, a fraction of the beam will go up and a fraction of the beam will go down. But if it is a single photon, once again, it will not be split in two. Either it will go up or it will go down. And in a certain situation, described by a certain wave function of state, as we say, we can calculate the probability. And so it is where happens or comes a new feature of quantum mechanics. It makes probabilistic prediction. You have no choice, because once again, a photon is not going, it's because of quantization. You can only have this or that. You cannot have any intermediate situation. So we need to have probability to describe what we expect. Okay, now you know almost everything in quantum physics. I can add a few things. This wonderful notation by Dirac describes a pair of photons both polarized along x. So I have a pair of photons both polarized along x. If they arrive on the two polarizers along this direction, you get +1, +1. Y is a pair of photons polarized along y, perpendicular to the screen, okay? And if they do that, boom, you are going to find them in -1, -1. Okay. Now, what Einstein and his colleagues discovered in 1935 is that if this allowed, if there really exist pairs of photons doing that, and if that also exists, so you can have pairs of photons doing that, then the sum of the two can also exist. And you are going, what is special about that pair? What is special about that pair, people who know a little bit of mathematics can easily demonstrate that this you cannot factorize. And the fact that you cannot factorize means that these states, you cannot say that it is, for instance, a photon like that and a photon like that. You cannot speak of the property of each photon. You can speak only of the property of the ensemble. It's both this and that. Maybe you are not yet surprised. So let me tell you that conceptually, it's as strange and bizarre as the Schrödinger cat, which is both dead and alive. Well, except that there is only two particles, okay? In a cat, there is more than two particles. But conceptually, from the mathematical formalism point of view, it's as surprising to have the superposition of these and that. And you will see that indeed the result of the calculation are not simple. So what do the calculations tell us about the result of the measurement of the polarization that we do on that state? First, it tells us that when you look at individual probability, that is to say, what is the probability to get +1 and -1 if the polarizer is in orientation A? Well, it tells us 1/2. Same probability to have +1 and -1, whatever the orientation of the polarizer. Same on the other side, okay? Same probability to have +1 and -1, whatever the orientation. Well, not very exciting. Hold on. Joint probability. Probability to get +1 here and +1 here. Or probability to get +1 here and -1, etc. That's a joint probability. I have a circuit, as I told you, coincide. I can tell you, oh yes, there is a detection here and there. This joint probability tells us that if I have +1 on one side, I have +1 on the other side for two parallel polarizers. If I have -1 on one side, I have -1 on the other side. This is what we call total correlation, but so strongly correlated, okay? There is a full correlation between this result here and this result there. And this is what I also called a tricky coin toss. And I want to emphasize that. You look on this side here, and you see a guy tossing a coin, head or tails, okay? +1, -1. Same on the other side, okay? You have somebody throwing a coin. So you see, oh, looks totally random. You look here, oh, it looks totally random. But if now you look from the middle of the auditorium, and you say, but this is unbelievable. When he gets head, the other one gets head. When he gets tails, the other one gets tails. It's totally correlated. There is a trick. You want to understand where is the trick. And that is my point. I want to have an image for that trick. Okay. The calculation telling us that there is a totally correlated result is based on the calculation, is a standard calculation. So I look at the calculation, say, can I make an image? Can I understand the trick by looking at the calculation? And the answer is no. Because if I want to make an image, I have to think of one photon separately with the other photon, while the calculation is made globally for this mathematical object, which is xx plus yy. And so I know exactly how to do the calculation in abstract space, but when I want to do an image in my space, to extract an image in my space, coming from that mathematical abstract space, I don't know how to do. Well, at the end, I will show you that there is a way to do it, but it is a little more involved. For that time, the simple way of doing the calculation doesn't provide an image. On the other hand, as a famous theoretician in quantum physics writes, quantum phenomena do not occur in a Hilbert space. They occur in a laboratory. I have a laboratory. I have a source. I have a detector here. I have a detector there. And I want to understand. So my two photons are emitted, they propagate. I want to understand what happens. Okay. At this point, in order to obtain an interpretation in real space, we can think of the conclusion of the paper of Einstein, Podolsky, and Rosen. They realized, it was not exactly their scheme, but they realized that really absolutely surprising correlation between this result at a distance. And they say, look, there is a simple way to understand that. The two particles have been prepared together. Just assume that they have a common property, and this common property is going to determine the result here and the result there. Think of the two guys throwing coins. If the coins were given by somebody in the middle, maybe the guy in the middle gives a coin with two heads, so they throw, they find head. Maybe the next one is two tails, okay, and then he throws two tails. Well, It's a natural explanation to say they were prepared together, so something common has been given, and it allows to explain. So you introduce a supplementary property that some people called hidden variables. Why hidden variable? Because these do not belong to the mathematical formalism of quantum physics. So this image is simple and convincing. I suppose there are some medical doctors in the room. Even before people could read the genetic code, when they are twin brothers having exactly the same disease, they concluded that the origin of the disease was genetic and the fact that they have the same chromosome. So this is just to emphasize the fact that this is real science. It's a scientific conclusion. You know, medical science is a real science, right? Okay. Sometimes. Why did they have a strong discussion, a strong opposition by Niels Bohr? Because this amounts to completing quantum mechanics. In quantum mechanics, all the pairs are described by the same state, XX plus YY. But here I say, oh, some pairs are like that, other I like that, etc. So I introduce supplementary parameter. And Niels Bohr had a deep intuition that you cannot complete the formalism of quantum mechanics. If you do that, at some point it will collapse. It will show an inconsistency. But, well, we'll see at the end that Bohr was right, but he was not convincing at all. I mean, his reply to Einstein that you can read, it was Physical Review. You find that easily on internet. It's in Prola, okay, in a basis of old papers. You read it, and you see that really it's philosophy, epistemology. You are not allowed to speak of quantities that you do not measure. Come on. At the beginning of the 20th century, there were plenty of people saying, you are not allowed to speak of atoms because you don't see the atoms. But thinking of atoms was extremely successful for Maxwell, for Boltzmann, for these people. So the argument that you are not allowed to speak of something that you don't observe, you may swallow it, but I don't swallow it personally. Okay. So Bohr disagreed with Einstein. It was more a discussion of epistemology, and it never ended. By it never ended, I mean they never settled the debate until their death. Okay, they never agreed on any compromise for that. Okay, Einstein was still maintaining his position, and Bohr was still saying, "No, you cannot do it," and nobody cared. Why? Because young physicists were using quantum mechanics successfully to describe plenty of things observed in the lab for doing theory, etc., etc. It was very successful. But I think that the main reason why people did not care is that because people realized, well, most of the people didn't even think of it, but the one who thought of it knew or observed that it was a debate about interpretation. In other words, Einstein did not disagree with the calculations. He said, okay, the calculations are right, the algebra is right. It was about interpretation. Einstein said, in order to understand your probability, you have to introduce a level, which is below. And Bohr said, no way, you cannot do it. But a matter of interpretation, you use the formalism, nobody disagrees on the formalism, so use it, publish papers, observe phenomena, publish paper, and everything is nice. All that until, so you see, Einstein died in 55, Bohr in 62, and in 64, John Bell made a fundamental discovery. He discovered that if you take the point of view of Einstein, you can write inequalities that we call nowadays Bell's inequality, and these inequalities limit the amount of correlation that you can have between the measurement. What do I mean by the amount of correlation? If the two polarizers are parallel, the correlation is total. But if you have an angle, you have a certain probability to have plus plus, a certain probability to have minus plus, etc. And so you can write a number which is the rate of the level of correlation. It's a standard definition for people who do statistics. Nothing to do to quantum mechanics. Okay? You have a random variable, and you just can define the amount of correlation between your random variables. Okay? And so Bell told you, look, when you change the orientation of the polarizer, if Einstein is right, the level of correlation cannot exceed a certain limit that we call Bell's inequality. I'm not going to demonstrate it now because it's not supposed to be a specialized talk. Okay. So now you have a quantitative disagreement. It's no longer a matter of interpretation. You have a quantitative disagreement between the point of view of Einstein and Bohr. Because if Einstein is right, at one moment, the prediction of quantum mechanics go beyond the limit of the, sorry, I speak too fast. If Einstein is right, the level of correlation cannot exceed a certain limit. But on the other hand, there are certain situations, and especially when you move the polarizer, when you make several measurements at several orientations of the polarizer, certain quantities go beyond the limit of Bell. So either quantum mechanics is right even in so extreme situation at EPR, or Einstein is right, and when we do the experiment, we are going to discover a small corner in which quantum mechanics is not true. Why do I say that? Because, you know, there are people who tell you, oh, theory are right until the day when they are wrong. It's not at all working like that. You have a theory working, for instance, Newton mechanics, classical mechanics. And then, one day, you come to a situation never observed before. Particles going close to the velocity of light and something. And then Newton mechanics no longer works. So you have to invent something new, which is relativity. It does not mean that Newton mechanics is wrong. Newton mechanics still allows you to understand the motion of planets. It means that in some extreme situation, it's no longer true. And actually, classical mechanics is a particular case of the whole relativistic mechanics at low velocity, period. So, you know, people saying, oh, you are not going to find that quantum mechanics is wrong in such a specific situation. Why not? It can be true almost everywhere, except in some extraordinary situation. So this is why it was interesting to do the experiment to check that corner of the world. There were 3 generations, so we can settle the debate by an experiment, and there were 3 generations of experiment. The first generation, between 72 and 76, first Clauser, who received the Nobel Prize in 2022, he found quantum mechanics. He was in Berkeley. At the same moment, a group with Pipkin in Harvard found agreement with Bell's inequality, no violation of Bell's inequality, so disagreement with quantum mechanics. So opposite result between, I insist, between East Coast and West Coast of United States, okay? Do you have something like that here between East Coast and West Coast of Iberic Peninsula? Okay, but at the end of these years, there was a trend in favor of quantum mechanics. The score was 3-1 in favor of quantum mechanics, but the experiments were definitely different from the ideal scheme, and this is why in 1975 I embarked into a series of experiments. So this is John Clauser, young John Clauser, okay, in 74 or 5, here in his laboratory. So I embarked in 74 into a new series of experiments. So you saw young John Clauser, now you see the young Alain Aspect here, okay, in my lab. So what was new in our experiments in Institut Optique in Orsay? First, we were able to develop a new source of entangled photon with unprecedented efficiency, more source, more pure, etc., etc. To make a long story short, in 2 minutes, we could make measurement as good as Clauser in many hours. So even theorists like Yasser knows that if you can do an experiment in 2 minutes, it's better than 2 hours. Okay, Yasser? Yes. He confirms, okay. But we could, the most important, with this fantastic source, we could realize schemes close and closer to the ideal experimental scheme on which theory is reasoning. So, for instance, this really resembles the schemes that I have shown, in which you have a polarizer with channel +1 and -1. In all other previous experiments, they only had polarizer transmitted one channel, but the other one you could not see. So you have to go to indirect reasoning, etc., to test Bell's inequality. So for the first, I told you, I wanted to be close to the ideal scheme. Here I am close to the ideal scheme. And there was something new, really totally new, by using here a switch, two polarizer. This mimics a single polarizer that you switch rapidly from A to A prime, A prime, A prime. By doing that, we could demonstrate what is now called quantum non-locality. That is to say, the fact that until the last moment, it's not decided what will be the result of the measurement. And it is only at the moment of the measurement that you know if it will be +1 or -1. Same on the other side. I will come back to this non-locality later, but the fact that we were switching that very fast, faster than the time it takes for the photon to go from the source to the polarizer, demonstrated that what is decided at the moment of the measurement is decided at the very last moment. Okay. It cannot be determined before. Okay. Third series of experiments, starting in the ends of the 80s and with real important progress in 98. Nicolas Gisin in Geneva. Well, what happened is that several groups of physicists were able to develop new sources of entangled photon better than mine. Mine was better than the one of Clauser. Their source was better than mine in the following sense. The two entangled photons were emitted in well-defined direction. So you could put them into optical fibers, and then you can stretch optical fibers over hundreds of meters or even kilometers. For instance, Nicolas Gisin here in Geneva was able to introduce a photon in Geneva, here at Bellevue, to make a measuring station at Cornavin, which is a village of like 4 kilometers, I think, from Geneva, another one at Bernex, like 10 kilometers from Geneva, and he still observed entanglement at such large distance. At the same moment, Zeilinger in Innsbruck used specific fiber, only 200 meters, not kilometers. But what he did, which was really a thing I had dreamed of doing but could not with the technology that I had in '82, he could operate a random number generator while the photon is in flight to select randomly the direction of the polarizer. I was not selected randomly. I was switching from A to A prime as fast as I could, but it was not like throwing a dice. It was not like a random number generator. So it was a real progress, and he confirmed that, indeed, the decision is made at the last moment, at the moment of the measurement. Okay. So Einstein's local realism is rejected by all these experiments, and let me explain a little more what is this point of view of Einstein, which turns out to be not supported by experimental result. What does it mean to abandon Einstein's point of view? Well, it's enough to read Einstein to know. So here, if you follow, you should be surprised. You say, Einstein did not believe in his own point of view? Yes, of course, he believed in his own point of view. But he tried to demonstrate that he was right. And for that, he was doing a reasoning ad absurdum. He was saying, if I was not right, this is what you would have to accept, to swallow. And it is so unbelievable that I am right. Well, let us see what he says that we have to accept. These are sentences of Einstein. He says, if I was not right, you would have either, I will comment after, okay? You would have, because these are the words of Einstein, you would have to either abandon the independence of the physical realities present in distance volumes, or accept that the measurement on one particle modifies instantaneously at a distance the real situation of the other one. If you think of it, it's not so different. Because if this interacts instantaneously with that, how could you speak of separate systems here and there? But anyway, he insists on having two different sentences, and in fact, it turns out to be extremely fruitful, because the first point of view, the idea that when I have two particles, the property of the pair is more than the sum or than the reunion of the property of the first one and the second one, the fact that it is more, we call it holism. And it is at the root of quantum computing. On the other hand, the fact that if I do something here, it can change instantaneously what happens there. This is called quantum non-locality, and this gives all this application called quantum transmission, quantum propagation. Well, I miss a word, it will come again. Okay. So the first one, quantum holism, leads us to quantum computing, and the other one leads to quantum communication. Now, well, by the way, even if we have non-locality, we cannot transmit an utilizable signal. If you want to know more, ask me a question at the end. Okay. Now, I will just take one example of how going to one of these concepts to some quantum technology, some application. And my example is how quantum non-locality allows us to well understand quantum cryptography. What is quantum non-locality? I already said it. It's the fact that the result of the measurement takes place at the very last moment, and until the last moment it was not determined, and this is true on both sides. In fact, there is a quantum calculation which allows me to see that it's a little more complicated quantum calculation where I suppose that I first do a measurement on the first photon. So I suppose, for instance, that this polarizer is closer to the source, okay? So I do a measurement on this one, and I know, you remember, I can have as well +1 or -1. If it is along x, +1 corresponds to x, -1 corresponds to y. I start with that, and then what do I do after I've done the measurement? I go to the Bible. Well, my Bible is a book, maybe some of you know it, by Cohen, Tanuji, Dieu, and Laloe. So I go to the Bible, and they tell me, just after a measurement, you obtain a new state, which is a projection of the initial state onto an eigenspace, corresponding to the result of measurement. Complicated words, which tell us that if I find +1, after the measurement, the pair of photons is described by the simple thing XX. Ah, now I understand. X, of course, I have found X. But the other one is X. So I understand that I will get +1. Okay. If I find Y, then the projection gives YY. So Y, of course, I get -1, but the other one is Y. And with this, I can indeed understand that when I do the measurement on the other one, I find the same result as the first one, and even for the angle, I find the same result as predicted by the most complicated calculation. So these allow me to really have an image for the total correlation at a distance. Okay? So this image yields the same result as the calculation in the abstract mathematical space. But you know, it's really strange. It's a kind of thing that Einstein could not accept. Until the moment of the measurement on the first photon, you can get as well +1 or -1. But if you get +1 instantaneously, you get +1 here. This is quantum non-locality. This is what Einstein could not accept, but we have to accept it. It's the fact that the measurement on the first photon seems to influence instantaneously at a distance, the state of nu2. This is called quantum non-locality. Why do I say seem? Because some people don't accept that. And when you ask them, what is your image? They say, I have no image, because I don't accept the idea of physical reality. If you don't accept the idea of physical reality, it's called, that's a school which is called shut up and calculate, which is the most, which is a favorite school of people doing calculation in quantum optics, although it changes now. But for a long time, it was really, people say, don't ask questions. Shut up and calculate. You have the result. You compare to the experiment. It works. What do you want more? OK. I want an image, and this image for me is quantum non-locality. Why do I like this image? It's because it gives me intuition of things which are quite sophisticated, which is called quantum technologies. I will give you only one example with quantum cryptography, but there are several examples of them. Quantum cryptography. Two friends, Alice, you recognize her. And Bob, you recognize him, okay? There was a song, I think, by Bob Marley at the beginning, when I arrived in the auditorium here. Something like a reggae song or something like that. Okay, they want to exchange a message, and there is an eavesdropper, the spy, who wants to intercept the message. And there is a method, cryptographic method, for having an absolutely sure communication, which is the following. Nothing quantum at this stage. Is a method invented by Robert Shannon, the father of the theory of information. It's called one-time pad. The idea is the following. Alice has a random series of 1 and of 0, and she used that to encode bit after, to change bit after bit the message. Bob has exactly the same series of 1 and 0, okay? He uses that, and he recovers the initial message. And it's demonstrated as absolutely sure. When I say demonstrated, these people are mathematicians. You know, they are serious, not like physicists, okay? They do real demonstrations, okay? Real theorem. And so these theorems say, there is no way to decipher it, except that there is a condition. You know, in mathematical theorems, there is always condition. The condition is that the length of the message should not be greater than the length of the coding key. And so the problem is to distribute to Alice and Bob, who are far away of each other. The problem is to distribute to them two identical series of 1 and 0 without the spy being able to get a third copy of it. And the key will be, the solution will be quantum K distribution. Quantum K distribution is about giving to Alice and Bob two identical random series of 1 and 0 with the spy being able to obtain a copy. And those of you who have really well followed can guess that what will be the solution? Entangled photon. If you have a pair of entangled photon, this is a modern source of pair of entangled photon. If Alice and Bob have the same direction for this polarizer, until the last moment, you don't know if it will be +1 or -1, but if you have +1 here, you have +1 here, and minus also. Which means that there is nothing to spy here, because the result is not yet decided. At this point, it's not yet decided if it will be +1 or -1. How do I know that it is not yet decided? Because of the violation of Bell's inequalities. If it was already decided here, you would not have a violation of Bell's inequality. So all that is consistent. So that's the idea of the method of Arthur Eckert. Was your boss, no, for you? He was his advisor for his PhD. Good idea to have Arthur Eckert as a... Yes, he was a very good, he is still a very good physicist. So this is a method invented by Arthur Eckert, okay? And you can make complicated calculation to demonstrate that it is secure, etc., etc. But my point is the following. Because I believe in non-locality, or I should rather say, because I like to use image like non-locality, I can immediately understand where there is no possibility for the eavesdropper here to steal the key, because the key does not yet exist. Okay. So this is what is written here. Okay. Our friends, Chinese, you know, they are very pushy. They have demonstrated entanglement at 1,200 kilometers by sending entangled photon from a satellite and sending it to 2 stations separated by 1,000 or 200 kilometers, okay? And now, there is somebody in the assistance who wants to work or works already in quantum memories. Let's suppose you have a good quantum memory. You put it in the satellite. You send the first photon, and you keep the second one in the quantum memory. You let the satellite go, and when it is at the antipode, you send the second photon. And now you have 2 entangled photons on the 2 opposite sides of the Earth, okay? So this is really fascinating, and there is plenty of prospects of really using quantum cryptography and other methods based on entangled photon, like quantum teleportation. I don't say more about quantum teleportation, but because I can let you dream, but you can ask me a question. Honestly, quantum teleportation is not taking Yasser here and sending him to my lab because I like what he is doing, okay? No, I cannot send him by quantum teleportation, but if you ask me a question, I will explain a little more about quantum teleportation. So this is the second quantum revolution. The second quantum revolution is realizing that entanglement goes well beyond wave-particle duality, which is something I heard all the time when I started my work. You know, Alain, you are just willing to demonstrate wave-particle duality. No, wave-particle duality is about one particle. Entanglement is about 2 or more. So now, anybody realize that entanglement opens many new possibilities, and you have a group here working on this possibility, on quantum technologies, okay? But I would like to remark that the second quantum revolution would not have been possible if it was not something else, which is the fact that physicists, starting in the 1970s, so I was already born for a long time, in 1970s, physicists became able to observe and manipulate single quantum objects. Before 1970, most of the physicists thought that quantum mechanics is only about large ensemble. I have a large ensemble of atoms, I shine light, I observe the emitted light, and then I have statistics, probability, no problem. But in 1970, for the first time, Hans Dehmelt was able to trap here in a trap a single electron and observe it for hours and even days, okay? And measure things on it and keep it. It's always the same. And then Don Eigler in IBM was able to manipulate single atoms and observe them. With Grangier, we were able to produce single photon and to observe wave-particle duality. Plenty of experiments. Serge Haroche, with his infrared photon, was able also to observe them individually. Immanuel Bloch in Munich observed single atoms. It's called the atomic microscope, etc. And even in condensed matter, well, with supraconductors, people are able to design circuits which behave like individual quantum objects, okay? And there are also envy centers, defects in silica, etc., etc. Okay. So to conclude, now we have quantum technology, which allows us to go from concept by using individual quantum objects. It allows us to go from concept, entanglement, to application. So what do we have? We have quantum communication. I gave the example of cryptography. Am I too long? Yes, a little too long. Yes, he said yes, so I have to finish. But I'm going to finish, so this is why I asked the question. Okay. Quantum communication. Quantum computing. Ask me a question about quantum computing. We don't have perfect quantum computers at the moment, but we have already imperfect quantum computers. And quantum metrology, which works very well. And so, to finish, will the new quantum revolution have a major impact on society? By the way, the famous quantum advantage, what is it? Calculating power, the fact that you can do calculation more difficult than with a classical computer? Maybe, but another side of the coin is maybe more efficient in energy. If I can do with a quantum computer the same as with a classical computer, with much less electricity, this is interesting. I think you have some research on that, and I think this is very important. Okay, so nobody can answer with certainty, but many believe in it. Many states, region, Europe, France, Région Île-de-France give money for the quantum program. I hope you have a quantum program in this country. At least you have a quantum institute, okay? Big companies which have plenty of money also work on that. I've seen on your transparencies that Deloitte is one of these companies who really have too much money, so they can afford to spend some money on quantum computing, right? And plenty of startup company, and we have fascinating perspectives. So young people, you have to know that it is an interesting field. And with that, thank you very much for your attention.
Thank you very much, Alain. This was a fascinating talk. There is now the ceremonies for the birthday of IST starting. That's why, as we knew, some colleagues from the leadership of IST had to leave as they announced to us. But we do have time for questions. Actually, when you asked me about time, I said you had more time, but this was perfect. So thank you very much. And now we have more time for questions. Yeah. So I think we have Gabriel and Constanza with microphones. So if you want to ask a question, or at least we have Gabriel, and we'll get Constanza. If you have a question, just please raise your hand and we'll bring the microphone. Please, Omar.
Hello, salut. Oh, sorry. Thank you so much for your presentation. It's really great to be able to see you in person and hear from you in person and see the importance of getting an image to pursue the research. My question, maybe it sounds a bit naive, but I was wondering if you ever experimented with the first two experiments from the wave-particle duality that were intended for single photons, but use entangled photons as the source for both those first experiments running simultaneously.
I'm not sure I fully understand the question. If your question is, did I do first an experiment with single photon and second an experiment with two entangled photons, it's just the opposite. Because in fact, the source for single photon is a byproduct of the source of two photons for the following reason. It's extremely difficult to produce a single photon, and the first method that was invented by us is what is called heralded single photon. We emit a pair of two photons. I detect the first one, and then I know that in a window of 5 nanoseconds, I'm pretty sure to have the second one. And although I have several atoms in my source, the probability is that in this specific window of 5 nanoseconds, the probability to have a photon coming from any other atom is totally negligible. So in that window, I have basically a single photon. While if I have a whole source, whatever I do, there is always some probability to have several photons because they come randomly from on the state. By observing the first one, in some sense, I stop the randomness because I see the first one, and now I know that the second is going to come. So in fact, the source we use was that one. It has been the only source of single photon for almost 2 decades, called heralded single photon. And then in the 2000, a new way to produce single photon has been invented in which you isolate a single quantum object. I told you, second quantum revolution is isolating single quantum object. So you isolate a single atom, or ion, you excite it and you wait. And then no choice, it emits one and only one photon. But in fact, it is in that order that it happened. We first use a source of 2 photons to invent the source of one heralded photon. I'm not sure that it was your question. Was it your question, or is not that? And then I have a second, then you have a second chance. Is it okay? Thank you. Because it might not be, is there a way to do, so I will answer to a question you have not asked. Is there a way to do quantum cryptography with single photon? Yes, it is another method, totally different, called the method of Bennett and Brassard. And the idea is to have a single photon and to encode the information, let's say, on the polarization, to make a long story short. So you can also do quantum cryptography with single photons. Another method, Bennett and Brassard. Eckert is with entangled photon, Bennett and Brassard with single photons.
Thank you very much. More questions, please? Just please raise your hand and we'll bring the microphone to you. Yes, I think there's a question there. Can you raise your hand higher so that Gabriel can see you more easily? Thank you. And then in the middle. Thank you very much. I've seen this conference where the microphone is in a foam cube and then you can throw the microphone to the audience. We should get one of those at Tech. Okay.
Thank you very much for the call, for the presentation. And I would like to ask, because with, thanks to John Bell's work, we now know that it's ruled out the possibility of hidden variables. But in the very latest years, someone is talking about superdeterminism or things like that, and I would like to ask your opinion about that, if there is something that you think is...
I'm going to tell you exactly what is superdeterminism, and you will choose for yourself what is your conclusion. But I will suggest mine. Superdeterminism is the following thing. It's a fact that when you have an experiment like that, okay, and you operate this random number, this polarizer, like in the Zeilinger experiment, you have a random number generator choosing the orientation. You have a random number generator choosing the orientation. And superdeterminism tells you, oh, you think that it is random, but it's not at all random because back in the past, there was something common which determines the result of that random number generator and that one. So if you accept this kind of explanation, then there is no point in being a physicist in order to discover the laws of the world, because everything has been determined at the time of the Big Bang, and it's finished, okay? That's called the Laplacian determinism. So logically and philosophically, you can accept this position. But in such a world, and now I just paraphrase John Bell, in such a world, I don't want to be a physicist. I am going to do something else. Who knows? Philosophy, maybe medical doctor is more... But, I mean, being a physicist in a world where you can explain everything by superdeterminism, I don't see the point. I think that I am free to choose the orientation of my polarizer. So that's my point of view on superdeterminism, but I admit that logically you can invoke superdeterminism to say, oh, look, it's not surprising.
Thank you.
Thank you very much. I think there was another question just in the back. Yes, please. Thank you.
So my question is about quantum holonomy.
About what?
Quantum holonomy.
Holonomy.
Holonomy. One of the things that Einstein said that
holism.
Yes.
Okay. Quantum holism. Okay.
So if you could expand more on that.
Well, okay. Again, Einstein thinks that you can speak of the physical reality of a system which is enclosed in a finite volume in space-time. So you have a finite volume in space-time, you have a system there, maybe several particles interacting between them, something like that. The idea of Einstein is that in that volume of space-time, you have all the parameters which allow you to know what will be the result of a measurement of energy, angular momentum, who knows, electric charge, etc., etc. And that it is really here. It can depend on things that you have done in the past. You have prepared the particles, and it determines what you have in the future. But it can certainly not depend on a knob that you turn here. And when I wave my hands like that, for people who know a little bit of relativity, I mean that it is separated by what is called a space-like interval. That is to say, if you want this to act on that, it has to be instantaneous. It has to be by a signal going faster than light. Einstein did not accept that. So Einstein thought that if I have a first system, there is a physical reality attached to this system. I have a second separated system. There is a physical reality attached to the second one. And Einstein thought that the two physical realities here really constitute the total physical reality of the system. The fact, the holism, quantum holism, consists of saying there is more in the reunion of the two objects than in the sum of this property and this one. And why is it so important for quantum computing? Because that is this idea which is under the fact that there is a huge amount of information that you can have in an entangled quantum object. Let me explain. If you have two entangled qubits, so a qubit can take value +1 or -1. For two entangled qubits, you have four possibilities, plus, minus, minus, plus, minus, minus. And so a state of these two objects can be projected on a space of dimension 4. If now you have 3 entangled qubits, you have 8 possibilities, plus, minus, etc. You count, that makes 8. If you have 4 entangled qubits, you have 16. If you have 10 entangled qubits, 1,000. 20 entangled qubits, you have 1,000,000. This is called exponential, okay? And so if now you have 100 entangled qubits, the size of the space where to describe that is absolutely impossible to think of. The dimension is more than the number of particles that you have in the universe, which means that the quantity of information that you can put in 100 entangled qubits is absolutely huge. And if now you do an elementary transformation, you do this elementary transformation on all your qubits, all these components that you have here, and this is called massive parallelism. This is what is at the root of quantum computing. Well, unfortunately, the world is not like that, because first, we don't have 100 ideal entangled qubits. We have 100 entangled qubits, but they are not ideal. So you need to have error correction, and for error correction, you must have many more qubits. That's the first thing. And the second thing, which is really annoying, is that if we give him tomorrow morning an ideal quantum computer, it does not know exactly what he can do with it. You can use a Shor algorithm, factorized number. You can use a Grover algorithm, search into a databases, and you have like 10 or 20 possibilities to use it. But there is no systematic method for using a quantum computer. This is why there are so many people in the world who work on that. They work not only on the hardware, but they also work on what would be a software to use cleverly, in a smart way, an ideal quantum computer. But to come back to the origin of your question, all this possibility of quantum computer stems from quantum holism, from the fact that for 2 entangled qubits, there is more information in 2 entangled qubits than in the sum of the information you have in the first and in the second one.
Thank you.
It was a long explanation, but I had no chance to explain quantum computing because I thought that he was cutting my time.
No. I wasn't. I confirm that we would not have any idea what to do if we had a full-fledged quantum computer tomorrow. So there's a lot more research that needs to be done also on the theoretical side, on the theoretical computer science, on the quantum algorithms.
Absolutely.
We are about to finish. Okay, one last question there. Thank you.
Okay, thank you for the presentation. You talked through the presentation that we are starting to have experiments with highly sophisticated theories and equipments and even experiments. Do you think that in a few years we might get to the point that we are working with such specific theories and niche fields that it becomes even difficult for other areas or scientists to even review the work in the first place?
Review what?
We might get to the point where the work is so specific that other scientists can't even review the work that has been done for other scientists in those niche areas.
This happens all the time. I mean, when relativity was invented, at one point somebody say, "Oh, there are only 3% in the world who can understand it," but now. Not everybody, but every student who has 4 years of university in physics can grasp a little, some significant part of relativity. Quantum mechanics is absolutely unbelievable. I mean, nobody could think of quantum mechanics until genius like Schrödinger, Heisenberg, Dirac developed the formalism. Now, any student who follows seriously his lecture after 3 or 4 years of university really can use quantum physics. So I think that it's a general evolution of things, that you have a new theory, and this theory becomes more and more familiar to more and more people. Nowadays, I think that engineers should have courses in quantum physics, because there will be quantum technologies, and engineers should better know quantum physics. So if it is your question, I have no doubt that it will become familiar. Well, Maxwell equation, electromagnetism. In 19th century, it was absolutely impossible to think of. People were saying, no, this is not possible, a field in the vacuum and something like that. Now everybody uses electromagnetism, build a transmitter, radio, television, cell phone, etc. So I am very optimistic for that. And I am very optimistic on another point. We don't know yet if we will be able to have, let's say, 100 ideal qubit entangles, which would demand, according to what we think nowadays, 100,000 real qubit, taking into account quantum error correction, etc. Sounds crazy, but we don't know any fundamental physical law saying that it is impossible. And I am an old man. My experience is that when something is not forbidden by a fundamental physical law, if it is interesting enough, sooner or later, it becomes possible. Engineers are extremely smart. Example, in 1990, there was a project of building big interferometer to observe gravitational waves. Sounded totally crazy, but there was no fundamental law saying that it is impossible. 20 years later, it was observed. And so I'm quite optimistic. It may take 20 or 30 years, so in that case I will not see it. But anyway, until the moment when we find a fundamental law saying it's impossible, I think that we can go ahead and go ahead.
Okay, thank you.
Right? Young people like him best.
I agree.
But
not that yet.
Do it rapidly. I would be happy to see it.
Me too. Me too. I also would like to see it. So I think we are now over time, and we wanted to respect the proposed schedule. So I just want to close the session thanking everybody. So first, thanking you for participating and for your interest participating so overwhelmingly. Thank you very much for Instituto Superior Técnico for hosting us on their anniversary day. Thank you also to the PQI team led by Herminia for all the organization of the logistics and the great work that the team did. And of course, most importantly, thank you so much, Alain, for coming, for sharing your knowledge.